Hi, in this video, I'll give a general introduction to speech synthesis. This lecture is part of the pedagogical project for CPSC 543, Natural Language Processing. An overview of the topic. Speech synthesis, also known as text-to-speech or TTS, is defined as the artificial production of human speech or acoustic waveforms from text input. Speech synthesis has a wide range of applications. Speech synthesizers can be used as accessibility aids to read out text for the visual impaired or to generate speech for the vocal impaired. For example, the technology is used in the Assistive Context-Aware Toolkit, or ACAT in short, designed by Intel Labs for people with neurological disorders. The system is used by the astrophysicist Stephen Hawking, who lost his voice due to ALS disease. ACAT allows him to speak by typing and the speech synthesizer speak out the words. Speech synthesis is also used in many modern applications, such as virtual assistants, including Apple's Siri and Microsoft's Cortana, and in smart speakers like Google Home and Amazon Alexa. It is also used in navigation systems in cars to read out driving instructions, and there's many more. As an overview, speech synthesis is a two-step process. The first step is text analysis, which is converting text input into intermediate representation. The second step is waveform synthesis, which converts the intermediate representation into waveform. So let's look at an example sentence. PG and E will file schedules on April 20th. So first step in text analysis, the non-standard words like the ampersand and the number 20, they are expanded to the actual English words and 20th. So this step is called text normalization. The words are then transcribed into an intermediate representation using what's called an alphabet. Alphabet is an English phonetic alphabet. This step is called phonetic analysis. We will take a closer look at the CMU pronunciation dictionary to see how this is done. The tone and accent of the sentence are then marked with asterisks and special labels in what's called prosodic analysis step. Notice at the end of the sentence, there's an L, -L% that indicates a final fall in tune. Finally, in waveform synthesis step, the intermediate representation is converted into a waveform shown at the bottom of this slide. This diagram shows the architecture of a unit selection synthesizer using an hourglass metaphor. We will talk about each component in more detail later. As mentioned, there are three steps to text analysis: text normalization, phonetic analysis, and prosodic analysis. For waveform synthesis, there are several different approaches. The first one is concatenative synthesis, which selects units from a database of pre-recorded speech and concatenate them together to form speech. Concatenative approach is the traditional and most widely used in modern systems. The second approach is parametric synthesis based on statistical models, such as the hidden Markov model, or HMM. The third approach is based on deep learning and neural networks, such as WaveNet and Tacotron. Both are developed by Google. We will take a look at several research papers on this most recent and cutting-edge technology. Next, I will talk about text analysis. This is the first part of speech synthesis. We'll look at text normalization, phonetic analysis, and prosodic analysis. Raw text need to be first pre-processed or normalized. The first task is sentence tokenization. Then we need to deal with non-standard words and also homograph disambiguation. In sentence tokenization step, the boundaries of each sentence is determined. The task is not trivial as one might thought, because periods are they don't always indicate the end of sentence. For example, in the example shown here, the group included Dr. J. M. Freeman and T. Boone Pickens Jr. So not all of these periods indicate an end of sentence. Some of these are used as titles, like in doctor, and some are just initials of persons' names. So period disambiguation is usually done with a classifier trained by supervised machine learning on a hand-labeled dataset. We can use logistic regression, SVMs, or a decision tree. The trained binary classifier will be able to determine two classes, end of sentence, EOS, versus not end of sentence. Some of the features that could be used in training include the prefix, which is the portion of the candidate token preceding the candidate, the suffix, which is the portion of the candidate token following the candidate, and also whether the prefix or suffix is an abbreviation or not. We can also look at the word preceding the candidate, the word following the candidate, and also whether those words are an abbreviation or not. So here's an example. For the sentence, ANLP Corporation Chairman Dr. Smith resigned. The features for the period in the word corporation would be, so the prefix is CORP, corp. There's no suffix, so it's set to now. The previous word, so the word that comes before corporation is ANLP. The following word, next word, is chairman. So ANLP is an abbreviation, so the previous word abbreviation is set to 1, and chairman is not an abbreviation, so next word abbreviation is set to 0. So these are the features that could be used during training. We can also use other features like the probability of a candidate occurring at the beginning or end of the sentence. Could also use case, because the sentence usually begin with capital letters for English. We can also use abbreviation subclasses like titles and months. So here's a decision tree diagram. It predicts either, so yes stands for it is end of sentence, no means it's not end of sentence. It uses features like probability of beginning or end of sentence. So this is B prop or E prop in the diagram. It also uses features like case of next word. So this is labeled as next in the diagram, and abbreviation classes. This is labeled as type in the diagram. So we can train a decision tree like this using CART's algorithm. Another problem we need to deal with during text normalization is these non-standard words. So this table shows different kinds of non-standard words. Like we have abbreviations, letter sequences, and acronyms that needs to be read as a whole word. And we have numbers, telephone numbers, zip code. So these numbers, depending on context, they need to be pronounced differently. And we have time, date, year, and also money, amounts, and also percentage. So a big problem with non-standard words is they are ambiguous depending on the context. So for example, numbers, this 1750, it can be pronounced differently depending on the context. So like if it's the year, then it's pronounced as 1750. If we're talking about like passwords, then its password is 1750. If we're talking about like money amounts, so it's $750 or $1,750. For our abbreviations, January 1st, this needs to be expanded into the full English words. For letter sequences like UN, DVD, PC, IBM, these are pronounced by just reading out each letter one by one. And for acronyms like IKEA, NASA, UNICEF, these are pronounced not by pronouncing each letter by letter, we are pronouncing them as if they were actual words. So dealing with these non-standard words require at least 3 steps. Tokenization to identify the non-standard words in the input text. Then classification, so to classify them into specific types, such as the table I showed earlier in a previous slide. Then we need to expand them into ordinary words. So let's take a look at how each step is done. So in the tokenization step, a splitter splits the words into tokens by looking for white spaces. And we can assume that anything not in a pronunciation dictionary is a non-standard word. Some words need to be further cut into combinations following simple rules. So we can look for hyphens or a change of case, like in to car. This needs to be split into to and car. And for RV, in this needs to be split into RV and ANG. Then in the classification step, their type can be classified according to regular expressions. For example, for years, we can use the regular expression shown here. Alternatively, we can train a classifier using machine learning algorithms. And for the expansion step, these are based on simple rules. So as we mentioned, so LSEQ, this is letter sequences, so it expands to a sequence of words, one for each letter. ASWD, this is read as word, so it expands to itself. Number, this expands to a sequence of words representing the cardinal number. And years, so NYER, these are years, so they expand to 2 pairs of non-digits. So like the year 2020, these are 2 pairs of number digits. So another problem in text normalization is that some words can be pronounced differently depending on the context. So for example, it's no use to ask to use the telephone. Do you live near a zoo with live animals? So I'm not a native English speaker, so you might not hear the difference for the first sentence, but for the second sentence, it should be quite clear. And 15 most common homographs in order are shown here. We have use or use, increase or increase, close or close, record or record, house or house, contract or contract, lead or let, leave or life, leaves or lives, protest, protest, survey, survey, project, project, separate, separate, present, present, read, and read. So again, I'm not a native speaker, so it might not be clear. Luckily, there's systematic relationships between homographs depending on their part of speech, like whether it's a noun or a verb in the context. So there's difference in whether the final consonant is voiced or not, like in use or use, close or close, house or house. There's also a stress shift for record, record, um, and also there's a difference in the whether the final vowel is weakened or not, like estimate or estimate. So different forms of homograph, they tend to have different part of speech. So this is good. So that means we can solve homograph disambiguation by solving a part of speech tagging problem. So to solve a pause tagging problem, we can use a hidden Markov model and the Viterbi algorithm. I won't go into detail on how this works because this has been already covered in 503 lectures. Next, we'll talk about phonetic analysis. This is the step that converts from words to phonemes. So a phoneme is just a unit of sound. This is also sometimes just referred to as a phone. There are two different methods. So we can either look up a pronunciation dictionary or use what's called grapheme to phoneme algorithm, or G2P in short. So the key element of the first method is a pronunciation dictionary. For example, the CMU pronunciation dictionary is a freely available one. So the dictionary maps words to their phonemic transcriptions based on an alphabet, which is an English phonetic alphabet. It consists of 39 different phonemes. Here's the URL that links to the online CMU dictionary. So in the example here, you can type in the words that you want to look up, and it will return the phonemes for each word representing how they are pronounced. And there's a Python package available for the CMU dictionary as well. It's called CMU dict. So you can just import this package and use these two functions. So CMU dict.dict, this returns a Python dictionary representing the whole CMU dictionary, and you can use it to look up individual words. And CMU dict.phones, this returns a list of the 39 phonemes. And in the assignment designed for this lecture, you will use this package as well to implement a simple synthesizer. So as mentioned, there are 39 phonemes in total, and vowels can carry a lexical stress marker. So 0 means there's no stress, 1 means a primary stress, 2 means a secondary stress. Consonants don't carry any stress markers. So here the table shows some sample pronunciations from the CMU dictionary. So you'll notice that for each word, it gets transcribed into a sequence of phonemes. So each one of those tokens separated by a white space represents a phoneme. So So looking up a dictionary might not always work because um, the size of the dictionary limits which words we can look up, and also we often have to deal with unknown or new words. So in that case, we can use a grapheme to phoneme algorithm. So this is an algorithm that converts a sequence of letters into a sequence of phonemes by guessing the pronunciation of words based on their spellings. Um, so it's based on an educated guess, so it's not always accurate. So early versions of the algorithm use handwritten letter to sound rules. So the rules they typically look like this. So you have A with B in square brackets followed by C and equals to D, and this means that B with left context A and right context C should be pronounced as D. So A, B, C, these are letter sequences, and D is a phoneme. So for example, if you have CI in square brackets followed by A, then the CI, they should be pronounced as sh. So as in association. A modern version of the algorithm train a decision tree or a neural network to learn these LTS rules. I won't go into great detail, but if you are interested, you can read the text-to-speech textbook, chapter 8.4, for more details. Next, I will talk about prosodic analysis. Prosody is the study of intonational and rhythmic aspects of language. Acoustic features are the subject of study. This includes F0, which is the fundamental frequency. So the higher the F0, the higher the pitch, intensity, and also duration, etc. So prosody often conveys the sentence level pragmatic meanings. There are three aspects of prosody: prominence, structure, and tune. So prominence is the idea that some words are more prominent than others, depending on whether they are pronounced. Structure is the idea that some words always tend to group together, or some others tend to have a noticeable break or disjuncture between them. Tune deals with the intonation of the whole sentence. And for prosodic analysis, the goal is to compute an abstract representation of prosodic prominence, structure, and tune. So for structure, we need to look for what's called prosodic phrasings, so words that tend to group together or that tend to have breaks in between. So that means we need to predict these boundaries or prosodic boundaries. So this can be solved as a classification problem. So we classify each division point as whether they are a boundary or not. Some implications of prosodic structure on waveform synthesis. So we often the final vowel of a prosodic phrase is longer than usual, and we often insert a pause after a phrase, and often there's a slight drop in F0 or pitch from the beginning of a prosodic phrase. Prominence, so to capture the idea that some words are more prominent than others, the idea of pitch accent is introduced. So these are linguistic markers that are associated with these prominent words. Tune is the rise and fall of F0 over time, and examples include a question rise or a final fall. So when we ask a question, there's usually a rise tune at the end of the sentence, and when we make a statement, there's usually a fall in tune. For example, on the left, it shows the statement, "You know what I mean." So there's a final fall in the tune. But if instead you say this as a question, "You know what I mean," then there's a rise at the end of the sentence to indicate this is a question. So there are more sophisticated intonation models, such as 2BI or Tilt. These models place these linguistic markers on the individual words and boundaries, like pitch accents, including peak accent, low accent, scooped accent, racing peak accent, step down, and also boundary tones like final fall, continuation rise, question rise, and final level plateau. So as a reminder, these appear in our intermediate representation, shown at the beginning. Like here, the L hyphen L percent, it's final fall, which means the sentence is kind of a statement. Okay, so recall that we have two steps in speech synthesis. We have talked about text analysis, which is converting text input to the intermediate representation. Next, we'll talk about waveform synthesis, so converting the intermediate representation into waveform. So there are three approaches: concatenative, statistical parametric, and end-to-end synthesis based on deep learning. For concatenative synthesis, we'll talk about diphone synthesis and unit selection synthesis. A diphone is a unit which starts in the middle of one phoneme and extends to the middle of the next phoneme. So it's used as the key element of diphone synthesis. So it generates waveform for a sequence by selecting from a pre-recorded database of diphones. These databases are constructed by recruiting a voice talent to read out each one of the combinations of two phonemes. As I mentioned, there are 39 phonemes, so that means there are 39 squared number of diphones. However, not all of them naturally appear in English. So in the synthesis step, we simply select these diphones and concatenate them together. But also we need to adjust for prosody using an algorithm called TD-Pistola. This adjusts the duration and the pitch. So to adjust for duration, so to increase the length, we duplicate part of the signal, and to shorten the signal, we remove part of it. To adjust the pitch, or F0, we'll resample the original signal to change the pitch. So let's look at an example. So TD-Pistola stands for time domain pitch synchronous overlap and add. So here we're trying to increase the length of a signal. So the algorithm does is it insert duplicated original signals to increase the length. Another example is changing the pitch. So here it's trying to increase the pitch. So the algorithm samples from the original signal and it adds them up together. But also it uses a Hanning window function which is a filter that smoothes out the artifacts when combining them. Um, and this combination will result in increased pitch. Next, we'll talk about unit selection synthesis. Unit selection synthesis uses a larger database that contains many copies of diphons. In diphon synthesis, the porosity of the concatenation is modified by TD-Psola, but no signal processing is applied to the concatenated units in unit selection, so it's not required. So we select the best unit, minimizing the sum of a target cost and join cost. And this can be done with a hidden Markov model. So we model the target units. They are the observed outputs. The units in the database, these are the hidden states. Then we can solve for the best path of hidden units using the Viterbi algorithm. So the target cost measures how well a unit matches the target diphon specification. On the other hand, the join cost measures how well the unit joins with its potential neighbor units. The target units are modeled as the observed outputs. So, and you can see in this diagram, the best path is labeled in bold, and it is learned by using the Viterbi algorithm. So here is showing the sequence of target diphons for the word 6. Next, we will talk about statistical parametric synthesis. Instead of memorizing the units used for selection, we can learn parameters to generate waveforms. It requires less memory than concatenative synthesis because the only information that need to be stored are the parameters of the model. So these models predict acoustic features from linguistic features. They are usually based on hidden Markov models. Usually at the end, they use a vocoder or voice encoder to generate waveforms from acoustic features. So here's a diagram of the general architecture of a hidden Markov model-based speech synthesis system. So an HMM is trained on a labeled speech database first. So in the training phase, speech parameters are extracted. So this include the spectral and excitation parameters from the speech database. The hidden Markov model is trained by performing a maximum likelihood estimation using the EM algorithm. Once we've done with training, then in the synthesis stage, given some text input after text analysis, a speech waveform is reconstructed from the parametric representations of speech. And this part is the vocoder, so the excitation, generation, and synthesis filter. This is the voice encoder. Finally, let's look at a different approach, so end-to-end synthesis. The idea is to learn a model directly from text input to wave features without going through the intermediate representations. So recent research explored the possibility of using deep learning. This includes Google's WaveNet and Tacotron. So WaveNet uses deep convolutional neural networks, the deep CNNs. So WaveNet, it combines the acoustic model and vocoder and produce raw waveform directly. So it can be think of as a neural vocoder. And according to Google I/O Developer Conference in 2018, WaveNet is already used by the Google Assistant on smartphones. Because WaveNet doesn't require the use of a vocoder, it can also be used to synthesize music instead of speech. So the model for the model, real human speech is used as inputs, and the WaveNet is trained to predict a probability distribution for each sample. It relies on these stacks of dilated causal convolutional layers. So these dilations allows the model to scale to different time steps. After training to generate a synthetic waveform, the network is sampled to draw a value from the probability distribution predicted by the network, and then that value is fed back again into the network to make a prediction for the next time step. So that's how it generates speech. For tacotron, I think the author mentioned they named the model tacotron because they like eating tacos. So this is based on an architecture using a sequence-to-sequence model with attentions. It includes an encoder shown on the left and an attention-based decoder shown on the right. And also there's a post-processing component. I think this is colored in green at the top. So the model takes in characters or character embeddings as input, and it produces what's called a spectrogram frame. So this spectrogram, they are converted to waveforms using a vocoder called a Griffin-Lim synthesizer. So tacotron, it combines the front-end text analysis and the acoustic model together. So that's why it can take the characters directly as input. So it uses these CPHG modules that are based on one-dimensional convolution neural networks and highway network and bidirectional GRUs. So as a summary, we have talked about the two phases of speech synthesis, text analysis and waveform synthesis. For text analysis, we talked about the normalization of text, the phonetic analysis, which converts normalized text to phonemes, prosodic analysis, which adds the markers for prosody, and then waveform synthesis, we talked about different approaches like concatenative, parametric, and end-to-end methods based on deep learning. I've glossed over a lot of details, but here are the references and pointers for further readings. The concepts presented in this lecture largely depend on the first textbook, Speech and Language Processing, an Introduction to Natural Language Processing, Computational Linguistics, and Speech Recognition. So I used the second edition of the textbook. The authors, they are working on the third edition, but the chapter on speech synthesis is not yet available. There's another textbook on text-to-speech by Paul Taylor. This book covers a lot of the details that I didn't cover. So these two books are a bit outdated. They're published around 2007. So for the recent methods like statistical parametric approach and the deep learning methods, it's beneficial to look at more recent papers like the ones cited here. And I borrowed a few slides from a course offered at Stanford. This is LSA 352, it's speech recognition and synthesis class. I think the instructor for this course is the author of the textbook, the first textbook. Yeah. So the learning goals for this lecture includes be able to identify the problems that need to be addressed during the text analysis step. Second one, understand the internal phonetic representation and alphabet. Third one, explain the differences between concatenative, parametric, and end-to-end synthesis. Fourth one, be able to perform basic signal processing to synthesize waveforms using Python. To assess each one of the learning goals, I have designed an assignment. There are 4 questions. So first one, come up with example sentences that might cause issues during text analysis, and then try the examples using a widely available TTS service such as IBM's Watson. Report any errors and explain how the issues can be resolved. So this question allows the students to gain some hand-on experience with real-world TTS service and help them understand the issue of non-standard words and why text normalization is important. Second one is practice using the CMU pronouncing dictionary to convert between the internal alphabet representation of words and plain text. So this is just an exercise on converting the 2 different representations. Third one is assigned readings. So students will be asked to write a brief summary of different synthesis methods and explain their differences. The final question is a coding assignment. So implement a simple concatenative text-to-speech program using Python. They will use the CMU dict package mentioned earlier and also a G2P package as well. And that is it. Thank you for watching. The next few minutes will be spent on answering questions. Next, I'll talk about the end result of the coding assignment, which is a simplified version of a concatenative speech synthesizer. So this is a Python script. And there in the file, in the starter code, there are 2 functions for the students to implement. So the function word synthesize and phone synthesize. So word synthesizes it synthesizes speech from text by concatenating words from a database, and phone synthesize it does concatenation of phonemes. I've already included the solution to these 2 functions in this file, so we can run this and see the end result. So we need to pass either an option -w, which stands for word concatenation, or -p, which stands for phoneme concatenation. So this will start a loop, and we can type the sentence that we want to synthesize. So for example, how are you?
How are you?
So this is using the word concatenation approach. And let's quit the script and let's try the phoneme approach. Let's try, just do it.
Just do it.
So it prints out the phonemic representation, and also writes um, the output files to a directory called waveforms. And that's basically it.